Hello, we are here to try to solve this claim. This claim, if A, B, C are integers and are all odd, the quantity delta equals B squared minus 4AC cannot be a perfect square. So how begins this claim? It begins with my comment, this comment, claim if A, B, C and are integers and have the same parity, then the quantity delta equals b squared minus 4ac cannot be perfect square. Is this claim true? If yes, prove it. So our friend Sahu wanted to know if we find the solution. Then our friend Black give us a hint, a very important hint. Can you find a quadratic polynomial with integer coefficients all of the same parity with integer roots? Then we have a correction by our friend Sahu. I think you mean rational roots, and this is the truth. So the hint here is to find a quadratic polynomial with integer coefficients uh, that have that doesn't have rational roots if the claim is true. Then our friend Sahu give us a counterexample with all even uh, coefficient, and he has reason. So we say ABC should be odd and coprime. So I corrected the claim saying that, let's say A, B, C are all odd, or if even we have D is a great common factor of ABC. So when we divide every coefficient by this GCF, we have all odd numbers. So it is the same to say now I am claiming that we want it to be all odd, that this delta cannot be a perfect square, and it is equivalent to say that a x squared plus bx plus c equals 0 with a, b, and c all odd integers. So we never rational roots. So let's prove, prove this claim. So we will proceed by contradiction. So I suppose x is a rational. So x equals p over q with GCF of p and q equals 1. So we replace x by p over q, and we have a p over q squared plus b p over q plus c equals 0. And so we multiply by so as I said, multiply by q squared, we have ab squared plus bpq plus cq squared equals 0. So we have two possibilities. P and Q are of the same parity or of different parity. If P and Q are of different parity, so P is even and Q is odd. Is that possible? Let's see. So we have this here, and we can say that because A, B, and C are odd, and P is even, so here is even plus odd equals 0. That is impossible because even plus even is even, and even plus odd must be odd, and 0 is not odd, it is even. So it is impossible. Because even plus odd equals odd. The same if P is odd and Q is even, we can see that it is the same. So we have only one possibility to continue with, that P and Q are odd. So we have the other possibility. So P and Q must be Let's see. So if P and Q are odd, so taking this equality, we can see that can be rearranged as AP squared equals minus Q PP plus PQ. And because P and Q have a GCF of 1, so Q must be divisible by A, or A is divisible by Q. So we can see that we have A equals some constant A prime times Q. And because both A and Q are odd, A prime must be also odd. And we can write that A prime P squared equals minus Q minus BQ plus P plus C. On the other hand, the same here, we can write it as TQ squared equals minus P factor AP plus Q. For the same reasons, and say that P divides C. So C can be written as C prime P. Because C and P are odd, so C prime must be also odd. And we can replace C by C prime P in this relation here. So we have A prime P squared equals minus PP plus C prime PQ. You can factor AP minus P P plus C prime Q. So we divide everything by P and we have A prime P equals minus P plus C prime Q. So we have finally B equals minus A prime P plus C prime Q, which is a contradiction because A prime is odd, P is odd, C prime is odd, Q is odd. So odd times odd, odd plus odd is even, and B is odd. So it is impossible. And this is the proof of our claim. Thank you for watching.